So today I will show you the final results for the search for the Neutrinoless double beta decay and some examples what other physics can be investigated with the data of GERDA. GERDA is an acronym for the germanium detector array. As the name suggests, it's using high purity germanium detectors. Those are enriched with about 87% in germanium-76, which is one of the isotopes where the standard beta decay is energetically forbidden. Thus, it decays from germanium-76 directly to selenium-76 via double beta decay and is therefore also a candidate for the Neutrinoless double beta decay. Using germanium detectors has some advantages. First of all, the detectors equal the source of the double beta decay. Hence, no dead material in the form of other detectors is needed. Furthermore, germanium is a very radio-pure material, which is important since keeping the background as low as possible is a key aspect to the GERDA experiment. Also, the energy resolution is smaller than 0.1% at the endpoint energy. This is important for good distinguishability between the end of the double beta continuum and the discrete peak which one expects for the Neutrinoless double beta decay. In GERDA, the detectors are biased over an N+ electrode, and the signal is read out via a P+ contact. Let's have a look on how GERDA is actually set up. We start with the germanium detectors, which are mounted into strings. Those strings form the full array of more than 44 kilograms worth of germanium. The array is then surrounded by the liquid argon instrumentation, which radially consists of wavelength shifting fibers coated with TPB and read out by silicon photomultipliers. In the Z-axis, light is collected by 3-inch photomultiplier tubes mounted to copper shrouds, which are lined with TPB-covered tetra tags. The copper shrouds are needed to keep the, in comparison, rather radioactive PMTs as far as possible from the germanium detectors. On the top, there are 9, and at the bottom there are 7 PMTs accommodated. The full payload is lowered into a 64 cubic meter liquid argon cryostat. The cryostat itself is placed in a 600 cubic meter water tank, which acts as an active Cherenkov neon veto. GERDA deploys several different types of germanium detectors. There is the broad energy germanium detector, BG, which has a very good performance but has very low mass. Hence, for reaching a large germanium mass, many detectors are needed and therefore also many possible radioactive cables to connect. The second kind of detector is the so-called semi-coaxial germanium detector. While it has a much larger mass than the BG detectors, it's not as good in performance. The newest type of detector is the inverted coaxial detector, which was added during the upgrade of GERDA Phase 2 in 2018. While the semi-coaxial detector has the P+ contact in the borehole, the inverted coaxial detector has, like the BG detector, a point contact. The design of this detector type comes with a good performance as well as a large mass. Now that we know the kind of detectors used in GERDA, let's have a look on the event topology these detectors can produce. On the left, you can see the events we are looking for, a double beta decay. Its topology is characterized by an energy deposition in a very small volume in the detector. This is called a single-site event, and only expected to be seen in one detector at a time. Now we have to distinguish these double beta events from other background events. For this, we have 3 methods in GERDA. The simplest one is the multiplicity. Here we can weight the events which deposit energy in several detectors by discarding all events which have triggered more than one germanium detector in the coincidence window. Other types of events like beta radiation and alphas on the surface of the detectors can be identified and weighted by means of pulse-shape discrimination. The last method we use in GERDA is the weighting of events which are in coincidence with the liquid argon instrumentation. The liquid argon instrumentation works as follows. If ionizing radiation is deposited in the liquid argon, scintillation light is produced with a wavelength of around 128 nanometers. This light is then absorbed by the TPB on the surface of the fibers and shifted to blue light. The blue light enters the fibers, is there shifted to green light and trapped in the fiber. The light is now guided inside of the fibers to their ends, where it is read out by silicon photomultipliers. If there is now an event in the germanium detector in coincidence with a signal from the CPMs, the event is discarded since a double beta decay event is expected to only deposit energy in a single germanium detector. The same is done with the signals from the PMTs, which observe the liquid argon in the z-axis. The performance of the liquid argon instrumentation depends very much on the quality of the liquid argon. Impurities on the level of a few ppm have already a large influence on the attenuation length and the tribute lifetime of the liquid argon, and thus also on the light yield and performance. The tribute lifetime can be used as an indicator for the purity of the argon. Pure liquid argon has a tribute lifetime up to 1.6 microseconds. A collision with impurities causes the tribute states to de-excite in a non-scintillating manner. This leads to a decrease in the tribute lifetime. As you can see on this plot, the tribute lifetime of the GERDA liquid argon was constant during almost its full time of operation at 1 microsecond. A mandatory check of the cryostat safety valves introduced impurities to the cryostat and decreased the tribute lifetime to 0.9 microseconds, at which it kept till the end of operations. After looking into the detector types and background suppression strategies of GERDA, let's have a look into the exposure. In this plot, you can see the full data taking period of GERDA phase 2. The colored bars represent GERDA's runs and show the exposure gained by each run. Along the x-axis, you can see the times GERDA took physics data in light gray. In dark gray, you can see the runs in which the germanium detectors were calibrated, so-called calibration runs. The red marks represent special calibration data, for example, data taken to characterize the liquid argon instrumentation. The black line shows the integrated exposure. At the end of data taking, the design goal of 100 kilogram years was surpassed with an exposure of 103.7 kilograms. Combined with GERDA phase 1 data, an overall exposure of 127.2 kilograms was achieved. Here you can see the final spectrum obtained from the 103 kilogram years exposure of GERDA phase 2. The light gray line shows the obtained data before any cuts. In dark gray, we see the remaining data after pulse shift discrimination cuts. And finally, in red, we see the events remaining after applying also the cuts from the liquid argon instrumentation. The blue line marks the Q value of germanium 76. The black line depicts the double beta decay spectrum. After all the background cuts, we end up with an almost pure double beta decay continuum, which can be used for the search of exotic physics. We will come back to that later. If we now zoom into our region of interest around Q beta beta, we find that in the analysis window, 13 events survived our cuts. We can quote a background index of 5.2 times 10 to the minus 4 counts per kV per kilogram per year, which makes the experiment quasi-background free, meaning the half-life limit is directly proportional to the exposure. Even with the one event, which we dubbed Primo, with only 2.4 sigma from Q beta beta, the assumption of no neutrinoless double beta decay yields the best fit result. We obtain a lower limit for the half-life of 1.8 times 10 to the 27 years at a 90% confidence level. The sensitivity turns out to be almost identical. Those results can be converted to an upper limit on M beta beta of 79 to 180 millielectron volts. This is dependent on the nuclear matrix element, which introduces the uncertainties. The plot also shows the limits set by GERDA in comparison to other searches for the neutrino mass, either in cosmology or in endpoint experiences. For cosmology, the result from Planck combined with baryon acoustic oscillations are given with smaller than 0.12 electron volts. Catherine's limit on the neutrino mass is 1.1 eV from the endpoint search in the beta decay of tritium. Now that GERDA is finished and its infrastructure is handed over to Legend, one can ask what is next. The ultra-low background approach from GERDA allows for physics searches beyond the neutrinoless double beta decay. One example is the search for super WIMPs. GERDA searched for superWIMPs in the mass range from 200 to 1000 keV in almost 59 kilogram years of exposure. In 2017, the threshold for the germanium detectors was lowered, which allowed the search for those dark matter candidates with masses from 60 to 200 keV in 14.6 kilogram years of exposure. On the top plot, you can see in dark blue the limit GERDA can set on pseudoscalar superWIMPs or axion-like particles. In the bottom plot, you can see the limit for vector superWIMPs or dark photons. Again, in dark blue, the GERDA limit in comparison to other experiments. As mentioned before, the pure two-neutrino double beta continuum achieved by GERDA allows for the search of exotic physics in it. A precise fit can be done here to detect possible distortions, which would be attributed to exotic physics. In the plot on the right, you can see how the emission of myrons or a Lorentz violation or the emission of sterile neutrinos would affect the shape of the double beta decay continuum in comparison to the standard one. The analysis of this data is ongoing at the moment in GERDA. Looking back over the last 10 years of GERDA managed to surpass all its design goals: 100 kilogram years of exposure, less than 10 to the power 3 counts per kV per kilogram per year of background, and to set a half-life limit above 10 to the power 26 years. With a final background index of 5.2 times 10 to the minus 4 counts per kilogram per kV per year, GERDA managed to stay in the quasi-background free regime, and therefore a linear correlation between the exposure and half-life limit could be achieved over the full operation time of GERDA. With a final limit on the half-life of 1.8 times 10 to the 26 years, GERDA came to an end and its infrastructure is now part of Legend. If you are interested more about Legend, make sure to watch Ralph's talk. The data accumulated over the years can and will be used to search for physics beyond the neutrinoless double beta decay. Thanks for listening.